In the early 1900s, Southern Pacific locomotive crews climbing the Sierra Nevada started disappearing into their own exhaust. The line crossed nearly 40 miles of snow, sheds and tunnels, and inside those enclosed spaces, smoke from a conventional steam engine piled up in the cab faster than a crew could breathe clean air. More than one engineer nearly passed out at the throttle. However, the fix wasn't a better tunnel, a bigger fan, or a redesigned boiler. Southern Pacific turned the entire locomotive around and ran it backwards, on purpose, for the next 50 years. Picture a normal steam locomotive. The boiler and smokestack sit up front, the cab and crew sit at the back, right next to the tender hauling coal or oil. That's the shape everyone pictures when they picture a train. It works fine in the open air, where wind carries the smoke away behind the engine as it moves. Inside a mile-long snow shed or a tunnel bored straight through granite, there's nowhere for that smoke to go. It just accumulates around the one place a human being is sitting. Southern Pacific's engineers realized the obvious fix looked backwards on paper, but was completely sound in practice. Flip the locomotive so the cab leads and the smoke trails behind. Baldwin built almost 200 of these cab-forward engines between 1928 and 1944 alone, all of them burning oil instead of coal specifically because oil could be piped forward from the tender to a firebox that was now at the front of the machine instead of the back. From the outside, a cab forward looked like it was being dragged down the mountain in reverse. From the crew's seat, it was the only version of the job where you could actually see where you were going and breathe at the same time. Diesel and electric locomotives solved the same underlying problem in a completely different way by making direction irrelevant in the first place. A steam engine is fundamentally lopsided. The firebox, the boiler, and the mechanical linkage to the wheels all live at one specific end. A diesel-electric locomotive is symmetrical where it matters. The diesel engine spins a generator, the generator feeds electric traction motors mounted directly on the axles, and those motors produce identical torque whichever way current flows through them. Run the locomotive forward or run it backward, and it pulls exactly as hard either way at exactly the same top speed. That single fact is the reason almost everything else about reverse running became possible on the modern railroad. Nobody has to engineer around a lopsided machine anymore. The machine simply doesn't care. That indifference is what makes helper locomotives work. Steep mountain grades need more pulling power than a train's lead engines can supply alone, so railroads add extra locomotives partway back in the consist or at the very rear, pushing rather than pulling, often facing backward relative to the direction everyone assumes the train is traveling. On the 12th of May 1989, a Southern Pacific freight train loaded with 69 cars of Trona started down the grade at Cajon Pass with two helper locomotives coupled at the rear. The crew had been told the train weighed roughly 6,150 tons. It actually weighed close to 9,000. Only 3 of the 6 locomotives on that train had working dynamic brakes, the electrical braking system that uses the traction motors themselves to slow a train down instead of relying purely on friction brakes that can overheat and fail. The train accelerated past 100 miles an hour on the descent, derailed on a curve, and ploughed into a neighbourhood on Duffy Street, killing the conductor, a brakeman, and 2 residents in their homes. The helper locomotives at the back weren't the cause. The miscalculated weight and the disabled brakes were, but the disaster is a permanent reminder of exactly how much force sits behind a train running downhill, and why the locomotives doing the pushing at the rear matter just as much as the ones doing the pulling up front. Modern freight railroads took that lesson and automated a chunk of it. A single freight train can now run 3 or 4 locomotives at the front and another cluster in the middle or at the rear, radio-linked, so the lead engineer controls all of them from one throttle without a second crew riding in the back units at all. Railroads call this distributed power. Spreading pulling and braking force along a 1.5 mile long train, instead of concentrating it all at the front, reduces the violent slack action that used to snap couplers and derail cars on long descents, the exact kind of force that contributed to disasters like Cajon Pass. Some of those mid-train or rear units run coupled backward simply because that's how they were left after their last trip. And on a diesel-electric locomotive, it doesn't matter even slightly which way they're facing. Passenger railroads solved a completely different version of the same puzzle. Commuter lines running into a city centre every morning and back out every evening used to need a way to turn the entire train around at each end of the line, which eats time and requires physical space the railroad might not have downtown. The fix is called push-pull operation. A locomotive sits at one end of the train, and a specially equipped cab car, essentially a passenger car with a driving compartment built into its far end, sits at the other. Heading into the city, the locomotive pulls from the front like normal. Heading back out, the engineer simply walks to the cab car and drives from there, controlling the same locomotive by wire from the opposite end of the train while it pushes from behind. Nobody uncouples anything. Nobody turns anything around. The locomotive runs backward for half of every single round trip, and most riders never once notice which end is actually doing the work. Some railroads went a step further and made backward the default. Early diesels had a long hood covering the engine block on one side of the cab and a short hood on the other, and a handful of railroads, the Southern among them, standardized on running long hood forward, treating what looked like the front of the machine as the rear for operating purposes. The stated reason was crew protection. In a grade crossing collision, better to have a few extra tons of engine block absorbing the impact than an unprotected cab. The trade-off was exactly what it sounds like. The engineer sat facing what most riders assumed was backward for the locomotive's entire working life, craning to see around the long hood on curves, all in exchange for a little more steel between the crew and whatever might be sitting on the tracks ahead. It's worth asking why every diesel locomotive isn't simply built symmetrical from the factory, cab in the dead center, controls facing both directions equally, the way high-speed train sets are. Some railroads have tried versions of exactly that. The honest answer is cost and flexibility. A locomotive with two full cabs weighs more, costs more to build, and burns fuel-hauling equipment that sits unused for half of every trip. Freight railroads run mixed consists constantly, swapping individual locomotives in and out of a lineup depending on which units are available and which ones need maintenance that week. Standardizing on a single, simple cab at one end keeps the fleet interchangeable. Any locomotive can slot into any train, in any position, facing whichever way it happens to be sitting on the yard track that morning. The flexibility of running backward when needed turned out to be cheaper than building every locomotive to never need to. High-speed and maglev trains barely bother with any of this, because most of them were designed from the start to be identical at both ends. A Japanese Shinkansen train set or a European high-speed set typically has a matching, fully equipped driving cab at both the front and the rear of the whole consist. So reversing direction at a terminal station means nothing more than the crew switching ends and walking to the opposite cab. There's no Y, no turntable, no push-pull cab car standing in for half the job. The entire train was simply built as two front ends stitched together, and running it backward relative to its last trip barely counts as a special case. It's just the other half of the same round trip. Braking is where the direction question quietly resurfaces, even on equipment that handles it well. A locomotive's dynamic brake, the same system that failed on several units at Keon Pass, works by turning the traction motors into generators, using the resistance of the electrical load they create to slow the wheels, instead of grinding friction brakes down to nothing on a long descent. That system works exactly the same whether the locomotive is leading or trailing, forward or backward. What it can't do is compensate for 6 locomotives being told the wrong tonnage in the first place. The mechanism was never the weak point, the information going into the mechanism was. None of this would be practical if turning a locomotive around were easy, and it usually isn't. The traditional method is a Y, a triangular arrangement of track that lets a whole train reverse its orientation through a sequence of backing moves, or a turntable, a rotating platform just long enough to spin a single locomotive in place. Both need dedicated land and time nobody particularly wants to spend. Plenty of short branch lines never justified building either one. Crews on those lines learned to run trains in whichever direction the track happened to point, coupling locomotives back to back in pairs so at least one always faced the correct way, or simply accepting that half the trip would run long hood forward with the engineer sitting sideways to see around the machinery ahead of the cab. Entire short lines operated for decades this way, and plenty of those same rural branches eventually lost their freight business to trucking and got abandoned outright, their unused Ys and turntable pits slowly filling in with brush. Freight yards run backward almost constantly, and it barely counts as unusual there. Building a train means sorting dozens of individual cars into the right order, and that job happens almost entirely in reverse. A switch engine backs a cut of cars onto one track, uncouples, pulls forward, backs a different cut onto another track, over and over, all day, every day. Yard crews call this switching, and an experienced switchman can read an entire yard's track layout the way a chess player reads a board, planning 6 or 7 backward moves ahead before the first car even rolls. Nobody in a yard thinks twice about which way a locomotive is facing. The question is only ever which track needs which car next. Running backward isn't free for the crew, even on equipment built to handle it equally well in both directions. Visibility is the real cost. An engineer facing forward can see the track, the signals, and anything sitting on the rails well in advance. Running in reverse, especially with a long string of freight cars trailing out ahead, that same engineer is relying on mirrors, cameras, or a second crew member stationed further down the train relaying instructions by radio. That's exactly why railroads put a second set of eyes, a conductor or a switchman, riding the leading end of a backward move specifically to watch for anything the engineer physically cannot see from the cab. It's a job that sounds simple from the platform and is genuinely uncomfortable in practice, standing on a ladder rung in the rain or the dark, relaying distances in car lengths over a handheld radio, while a few thousand tons of steel creeps toward whatever's around the next curve. Radios fail, batteries die at the wrong moment. That's why the hand signal system railroads used for a century, lantern swings at night, arm positions in daylight, never fully disappeared even after radios became standard. It's a low-tech backup for a job where the backup genuinely matters. So the honest answer to why some locomotives run backward on purpose isn't a single reason. It's a pile of separate, practical answers that all point the same direction. A century of steam-era crews needed to breathe. Modern diesel motors genuinely don't care which way they're pointed. Mountain grades need force pushing from behind as much as pulling from the front. Commuter railroads needed to stop wasting time turning trains around twice a day. None of it happened because engineers ran out of better ideas. It happened because, on a machine that was never going to steer itself anyway, which end faces forward turned out to be one of the few things railroads could actually choose.